Hello everyone, welcome to Adson Engineering Academy. It's me, your tutor Adson, that is to say Prestressed Concrete. So please, before I continue, do subscribe to my channel, hit the notification bell so that you don't miss any of my video. Whenever I upload a new video, you get notified. So let's dive in and see how to handle. Before we continue, allow me introduce you to what we are covering today. So in our video for today, we're going to look at what we call the concept of pressure line, or you can call it Thurst line concept. Okay, so before we proceed to solve any other problem, I would like to give you a few of the things that we're going to utilize. That is to say, the concept that you need to know before you proceed with this particular concept. Now, if this is my beam, this is a cross section of the beam, and as you can see, this is the center, the neutral axis, okay? So the distance from this neutral axis to where the tensional force is acting, that distance is called eccentricity, E. That's why it is denoted with what? With E, okay? Then, if it is from the upper side, they say the upper side, we have a force P that is acting at this particular line, and that is compressive in nature. So in this case, the distance from this neutral axis, from this part up to where the compressive force is found, we are calling it what? E dash. Now the total distance between these two forces is what we are calling what? A. So this is only possible when this particular beam is exposed to pre-stressing. Okay, that's why we have this pre-stressing force P equals to T in this case. Now we know very well that to get what we call moment is given by a particular expression of force times distance. And now if the force is C times distance is what? Is A, the total distance, okay? Or you can say it is T, if you're considering the downward one, times distance A, okay? Total distance. So this is the same as P times A. Now, if that is the case, P is equals to M is equals to P times A. If I want to get only A, it's going to be what? It's going to be M divided by what? By P. This particular expression is very important to us. Now back to the total distance here is A. So that means A is equals to E plus E dash. Okay. So if I need only E dash, let's say for instance, if I know A and I know the eccentricity, so because I can calculate A, if eccentricity is given, I can find my what? My E dash. Remember, that will help you in drawing what we're calling the Thurst line or the pressure line. So you need this particular value of what? E dash. Okay. So another thing is that if we substitute here, you find that A is M by P, then minus E. So this is how you get your particular value of what? Of E dash. Okay. Now, the thing is that we have the stresses that will be attained at the top of this beam, then at the bottom of this beam. And this stresses will be the summation of, at the top we have summation of stresses due to direct stress, that is P by A, then that due to pre-stressing force, that is PE dash by ZT. That means the section modulus at the top. Okay, then at the bottom we have stresses which will be the same P by A, and then here is minus. Remember, at the top is plus, then at the bottom is a minus. So PE by ZB. Now this is how we end up calculating the stresses at the bottom. Now let's have a look at a problem so that we can understand this particular concept very well. So this is our first problem that we are solving today, and the question says a pre-stressed concrete beam with a rectangular section 120 mm width and 300 mm deep supports a UDL of 4 kN per meter, which includes its self weight. That means both the UDL and the live load are combined in this. Both the self weight and the live load, okay, combined to be 4 kN. So take note of that when they say which includes self weight of the beam. Effective span of the beam is 6 meters, and beam is concentrically prestressed by a cable carrying a force of 180 kN. Locate the position of the pressure line in the beam. Well, so what do we know? So from the given data, we can proceed to calculate this very well. This is what we have, given that the force P is 180 kilonewton. The cross section is given to be 120 by 300. That means our cross sectional area, this is S. Okay, our cross sectional area therefore is equals to 120 times 300. You get 3.6 times 10 to the power 4 in millimeter square. Now we can also proceed and get section modulus. That is what Z, whether at the top or at the bottom. In this case, it is the same. BD squared by 6. So this is 120. Then our D, which is the depth, is 300. So we square it and divide by 6. The answer is coming to what? 18 times 10 to the power 5. So please do confirm this by pressing your calculator. Okay, so that you know that the answer is what? Is correct. So allow me to show you that how I've got that. I think it's a quite simple one. This is 120 times 300 square. Now we are dividing it by what? We're dividing by 6. So you realize that it is what? 1800000. So it is 18 times 10 raised to the power 5. So I believe that is understood. Well, the next is the UDL, which is given. It is a combination of dead load and live load, because they said self-weight is inclusive in the question. Okay, so that is 4 kilonewton per meter. Now we can proceed and get what we call the maximum moment at the center span due to this particular UDL. It's given by the formula of WL squared by 8. This is just like a simply supported beam. So the formula, once we substitute here, is W is 4. Then our span is L, which is 6 given. Then we divide by 8. So 4 times 6 squared divided by 8. Our answer is coming to 18 kilonewton meter. Now, since we know the moment, we can proceed and also get what we call the bending stress due to this UDL. And it is given by the expression moment divided by what? By Z. So our moment is 18 times 10 to the power 6. Why? This is in kilonewton. To convert it to Newton, you multiply by 10 to the power 3. This is in meter. To convert it to millimeter, you multiply by 10 to the power 3. In total, it comes to times 10 raised to the power what? 6. Okay, this is now Newton millimeter. Then we are dividing by Z, and our Z value, we found that it is 18 times 10 raised to the power 5 mm cube. So in total, remember, up is now Newton millimeter, and then down is mm what? Mm cube. So you realize that this one will reduce this to square. So Newton per mm square is the unit of the stress. So the answer is coming to 10 Newton per millimeter square. That's our stress. We can as well calculate direct stress, P by A. So P is 180 kilonewton. So you multiply by 10 to the power 3 to convert to Newton. Divide by area, which is 3.6 times 10 to the power 4. So we're getting this 5 Newton per mm square. What could be the resultant? Remember, this is at the center. So this is due to pre-stress. This is due to pre-stress. This one is due to direct stress, which is P by A, the first one. Okay. Then this one is due to the what? The bending stress due to the UDL that we calculated. Remember, we obtained that to be 10. This particular 10 here. So this is 10 at the bottom and top. What is the resultant? 5 positive, positive. Remember, I've done this in the previous videos. Please do watch it so that you can understand how these stress distributions are actually drawn. So this particular one is due to the loads. This one is due to the loads. Okay. So this is 5 plus 10 is 15. Then this is 5 minus 10 is minus 5. So you now understand why this diagram is drawn like this, because this minus 5. Okay. So remember, I gave you a particular formula at the beginning where we said stresses at the what? Stresses at the top is given by summation of this plus this equals to this one. So let's prove it out, whether that is possible to help us get the value of E or E dash that we need in our calculation. Well, now looking at what we call the stresses at the top. So I know P by A already, then plus P E dash by ZT. Why? I need to get this value of what? of EDAS. Okay, so if that is the case, because I'm not following the other way of getting A, I'm following this particular way to give me EDAS. Okay, so this is going to be P by A, where P is 180 times 10 to power 3 divided by A. So this is what you have. Then plus P is 180 times 10 to power 3, then divide by 18 times 10 to power 5. EDAS equals to resultant at the top, which is 15. Okay, so this one is 5, this one is 0.1 EDAS, and then this one is 15. So when you bring 5 on this side, you realize that it is going to be 10. So EDAS is 10 divided by 0.1. It's coming to what? It's coming to 100. This is our particular value of EDAS, and this is in mm. Okay, now most importantly, what the question is asking, you have to locate the what? Pressure line or the thrust line. So this is what we have. If we are drawing like this, remember this is at the center. What we calculated is at the center. EDAS is 100. At the support is 0, 0. Okay, so you draw it as a curve, maximum at the center, and then you come here. Many more we're still going to calculate, and you understand how we can do it at quarter span, how we can do it at support, how we can calculate it still at the center. So please don't miss the next video so that you can understand in detail this particular concept of thrust line. Thank you so much for watching this video till the end. If you like the video, if it's helpful, so please like, share, comment, and then above all, still subscribe to my channel so that you always get informed if the new video is uploaded. Thank you.